couple of hours to register to MRIs. Now, that's not really a big deal. You launch something, you wait a month, and your data is registered. But okay, waiting a month is not great. But if you only had to do it once, it wouldn't be a big deal. The problem was that we had this idea that we would develop these cool models to do things, and to develop the models to do research, we had to run registration over and over and over and over again. And so that was a very slow way to do things. Now, of course, if you want to deploy these in the clinic, again, runtime is important. So nowadays, we tend to use machine learning and the new registration tools, and they tend to be a lot faster. Now, this is great that they're faster. We can sort of launch something, go off to lunch, come back, and we've registered all of ADNI or something. And that's great. But the really, really cool thing that I'm personally excited about is that we can really explore new models to do new things. And so a couple of them you've heard about in my introduction, like building templates, which I'm going to cover a little bit of. And that, I think, really opens up what can be done in neuroimaging. All right, so the outline for the rest of the talk is there's really two parts. I'm going to cover registration just in a few minutes to make sure everybody is on the same page. I'm going to cover classical and machine learning registration. And then I'm going to talk about all kinds of interesting directions, well, what I think are interesting. And so obviously they will involve some of my group's work, but they're really about, I think, what are the new directions that we can explore that were really difficult before. So registration, just for definition's sake, when I talk about registration, I refer to having two images, for simplicity, two images. And what we care about is the deformation field or the correspondence field that connects them, right? It's a vector field that tells me at every location how I can warp one image into the other. And as I said, it's a fundamental problem. And so people have worked tremendously over the last few decades, and they've developed really, really awesome models and mathematical strategies to find this deformation field. And it most often revolves around this one equation that basically says, I want to find the best deformation field that matches up the two images and is in some sense regular. The deformation field should have some sort of anatomical consistency or something like that. And there's a lot of work on this, right? So people have looked at what's the best image matching term for different tasks? What is the best regularization term? How do we optimize all of this? It's awesome. So there's a lot we can learn, but it's a very slow process because every time we see two new images, we start the process from scratch as if we've never seen images before. And so I want to say about 4 years ago, these learning-based frameworks came about. And they kind of came at it from a completely different angle. They kind of threw away all of that prior work and they said, no, we're going to treat this as a black box. We're going to assume we have some black box that we can exploit, like a convolutional neural network. And we're just going to get two images and we want to get out the deformation field, right? So how do we train these black boxes? Well, usually we can do it in a supervised way, or at least that's how we knew how to deal with these things, right? So if we have some ground truth deformation fields, it's actually pretty easy to train one of these convolutions. We just take two images, we get the deformation field out, we say, no, this is wrong, this is what it should be, and the network adapts its weights. Now, the problem here that we had was that there really wasn't any exploitation of everything we've learned before, right? What about diffeomorphisms? What about really cool constraints on the images and on the, all of that has been thrown away. But these methods were really, really fast. And so they really kind of offered this opportunity because after you've trained them, all you have to do is feed two images into the network and you get your deformation field. All right. And so this is kind of where we were getting excited about it, and a bunch of other groups were getting excited about it. And we started to look at how do we build, how do we learn these networks, but we don't require ground truth, right? So that you don't go through the process of trying to get the ground truth deformation in some other way from some other software or from radiologists or something like that, right? So how do you tell a network that a deformation field is any good if you don't know what the deformation field should be? Well, it turns out we know how to do that very well from classical models, right? Because they've taught us, well, you just need this loss function, one that tells you, oh yeah, the images match or they don't match, and how smooth is the deformation field. And there's many varieties for that, but we can take all that from classical models, implement them in a differentiable way, and use them in our networks. And so now when a network gives us a deformation field, we can tell it whether it did a good job or not by simply using one of these loss functions. Now, of course, we're not optimizing a single deformation field anymore. We're optimizing the whole neural network. So we need to look at all the pairs in our data, or a big sample of them. So we need to sum. We're not optimizing the deformation fields. We're optimizing the neural network parameters. So we're going to propagate information through there. But really nothing has changed from neural network training except the loss, which we can take from classical models. We trained this neural network with stochastic gradient descent strategies, and there's all kinds of tricks that you can employ from the latest sort of architectures and things like that. But at the end of the day, it's a very simple technique. You get two images, you use your loss function, and you train your network. And once you've done that, it's actually really easy to register. You take your two images, you put them through the network, and you got your deformation field out. All right, so that kind of covers the way this sort of parts that I think are important for my talk about registration, the classical models and the neural network models. If you want to learn more about this, I'm going to do this sort of shameless plug. You can go to tutorial.voxelmorph.edu. It's a pretty thorough kind of Google Colab walkthrough registration in general. Or you can go to the Learn to Reg website, which is this tutorial we ran a couple of years ago that has morphed into a challenge. Both of these are excellent sort of for introduction to how learning-based registration works. All right, so now the question is, why am I so excited about this? What can we do with this? What are the properties of these networks, and what are the sort of directions they can take us into? So first, let's look at some properties really quickly. The runtime, well, they're really fast. Okay, there's these really awesome baselines, mostly that run on CPUs, classical iterative methods. You can tune them, you can make them faster or slower, more accurate, less accurate. But at the end of the day, they take tens of minutes to run on a CPU. And we all know neural networks, once they're trained, they're really fast, right? It can take less than a minute. Nowadays, we can take it down to about 20 seconds on a CPU, really fast on a GPU, even for really large volumes, neuroimaging. Okay, how do we know if registration is any good? Well, so throughout the rest of the talk, I'm going to measure dice of a warped segmentation map and a fixed segmentation map. So I get these two images, the moving and the fixed. I'm going to warp the moving image onto the fixed, and then I'm going to take manual delineations of structures and I'm going to propagate them over. If these structures match up after registration, that means I've done a good job. I've done some anatomically meaningful correspondence. And when we first look at the results of the very baseline, sort of basic deep learning registration method that we call VoxelMorph, the results are basically the same as classical models. You basically achieve the same accuracy. So here on the y-axis is dice, different structures that I'm showing you. They all kind of match up, right? Between the baseline in orange and the VoxelMorph in yellow. And so the conclusion was, okay, we can do as well as the classical models. That's encouraging, but we're much faster. So there's something to exploit there. But the first question we got all the time was, well, but don't you need thousands and thousands and millions of images to train these models? Because that's what we knew about deep learning. And so the interesting thing was that it turns out you don't. You can learn from very little data. So we did this very simple experiment. We trained a bunch of different models. Super vanilla models, okay? Small networks, no batch norm, no data augmentation, nothing. And we just took these small data sets, 10 images, 25 images, 50 images, 100 images. We trained different models. Then we looked at how well they performed compared to the state-of-the-art classical model. And after about 50 images, you already did almost as well. And again, there were no tricks. Nothing. So you actually didn't need these thousands and thousands of images. If you add tricks, you improve. In fact, you can use these models to initialize classical deformations, classical models, and get back to the state of the art in just a few seconds. So the reason I'm showing this is just to say, okay, so these models are fast. They're pretty easy to code. You have a lot of knowledge you can build on, and you don't need a lot of data. So it's a really, really cool area to work in because you don't need to download, all of ImageNet. You don't need to worry about supervision and so on. So you can test out ideas really quickly and potentially have a lot of impact. For example, one of the things we were really interested in is, okay, we want to register brain images, but what if we only care about the hippocampus? What if we want to do a hippocampal study in imaging genetics or in Alzheimer's or something like that? So we don't really care how well the cortex is aligned or something like that. Can we tell the network, hey, we only care about the hippocampus? And it turns out you can in a very easy way. If you have some segmentations at training, you can just give those segmentations to the network in the loss function. So now here, we're just telling the network, hey, you're only going to see the images. Okay, so the network doesn't get any more information than it ever did before, but in the loss function, it's going to learn to focus on the segmentations you provide. So we can tell it, hey, here are segmentations of the hippocampi from the images. Make sure these align really well. And so the network will now, without ever seeing the maps of the hippocampi, will learn how to register the images to best sort of align the hippocampi, which is really awesome. I think it opens up a bunch of possibilities, and I'm going to show you sort of lines of work from that. And that was also the first time we saw that we're not just matching the classical models state of the art, we can substantially improve on them. In this case, it was about 10 dice points. So it was sort of a really exciting time. And so we kept getting these questions, okay, well, how well do these models work in different instances and different problems? And one of them was really dealing with clinical data. Now, at McKay, we tend to work with these really pristine, really beautiful MRI images that we got from all kinds of different data sets, ADNI and the like, where images are acquired very carefully and they're clean and they're processed and all of that. So they look really nice, and that's really awesome. But clinical images are of a different sort. These are the images I was dealing with. They're slightly different, right? Lower resolution, a lot more noise, a lot more artifacts, there's motion, they're chopped off, all these sort of things. So the question was, how well can we deal with this? And this was important because during my PhD, we really could not deal with these images well. They break all of the classical algorithms because, well, they have all these properties, right? It's really hard to align images that look like this. But it turns out deep learning is a little more robust than we thought. In fact, almost out of the box, the voxel morph models that we trained did substantially better than really carefully fine-tuned networks. So, fine-tuned classical models. So during my PhD, we spent, I think, a year and a half fine-tuning the baselines really, really carefully. We got to about 72, maybe up to 75 dice points for some structures. And then we ran voxel morph with just changing the loss function, and we got 78. And I think the reason this is happening is because the deep learning models are not subject to the same local minima behavior as the classical iterative models because they get to see so much data. At every iteration, they get a different image pair. And so they're stochastic, and so they can get out of local minima much better. And so we were really excited about this because now we could work with our clinicians and register all these really large data sets of stroke patients to do analysis much faster, much better. But we were faced with this other problem, and it's a problem of that's sort of fundamental in machine learning, which is that these algorithms are only really good at the data they see. So if I train my model with T1 MP-RAGE cleaned up data, it's only going to work on those data, on those types of data. And so if now I want to use my voxel morph model on, let's say, registering to T2 data or T2 to T1 or something like that, it's going to break down. So in neuroimaging, we have a lot of modalities. We would really love to build models that can generalize substantially to any other modality that I throw at it at test time. I don't want to retrain my model every time. I don't want to fine tune the model every time. We certainly wouldn't be able to do that in the clinic. So how do we deal with this issue? And that's how we came up with this project called SynthMorph. And the idea was, could we synthesize the variability that we don't care about? In particular, could we synthesize images of such different contrasts, of such crazy, maybe impossible contrasts, that we teach the network to not focus on the actual contrast, but instead to try to extract the anatomical structures underlying the images. So let me show you what I mean. Here's what we start with. We start with label maps. So we don't require any real images at all, okay? We're just going to start with label maps. And the idea here is we're going to use these label maps to generate a world of synthetic data that is unbiased in contrast. So we're gonna start with these label maps. We're gonna warp them in some completely random way. We're going to then sample some intensities. Now, in this case, I'm putting white in the white matter and gray in the gray matter and so on. We're going to add noise. We're going to add all kinds of effects that we expect to see, blurring for partial voluming. We're going to add motion, bias field, all that sort of thing. And we're going to get some image. Now, this image looks somewhat realistic because I knew what intensities to put in to make it look realistic. But what if we generate just completely random contrasts? So here we're putting black in the white matter on one side and gray in the other. And we first did this for a segmentation project led by Benjamin Below, but now I'm going to show you how it works in registration. And so we start with an image map, or label map, sorry. We start with a label map. We generate 2 different label maps from there by randomly warping them. We generate these 2 crazy images that are not very realistic, and then we're going to feed these to the network. And so the interesting thing here is that we're starting with sort of label maps of the brain, but we are not synthesizing realistic contrast. So we're teaching the network to deal with any contrast. But then we thought, well, maybe the registration networks don't even need to see brain synthetic images at all. Maybe they can just see random shapes. And so we try to look at that. What if we just generate these random shapes, right? Random label maps, deform them, and fill in really crazy intensity, right? And the question was, can we get the network to register these images? Because if they can, then they will probably be able to register any modality we throw at it. So let's see what this looks like. These are the sort of brain images we create. These are the sort of shape images that we create. They're unbiased in a sense in anatomy. They're unbiased in a sense in contrast. And then we feed 2 of these images to the network. And we tell the network, well, give us a deformation field that matches up the images. How do we know if it does a good job? It's really hard to compare these images, but we know the segmentations that generated these images, right? And so we can tell the network, well, I'm only going to show you the images, but I expect you to match up the segmentations, because at the end of the day, what I care about is matching up anatomy. So the registration network needs to now learn to identify meaningful segmentations, ignoring the contrast, and register it. So how well does this do? Well, we trained 2 models. We trained this SynthMorph on shapes, and then we trained the SynthMorph on brains, but again, completely synthetic brains. These networks never see any real data. And then we're going to test on real data, real brain MRIs from different data sets. And so how well does this strategy do? I think it's very interesting to see kind of the behavior. Classical models in red do pretty well when you're registering a T1 image to a T1 image or a T2 image to a T2 image. The voxel morph models in green, when they're trained on T1 or trained on T2, they also do pretty well. In some sense, they do on par with the classical models, maybe a little bit better, a little bit worse. And then the synth morph models in blue, they also do the same. But let's look a little carefully what's happening here. The shape models, the models that only ever see completely random shapes, they do as well, basically as well as everyone else, except for maybe one voxel morph model. And that's remarkable because these have never seen any real data. So now we don't need any data to train these. And then if you start with brain segmentation maps, again, no real data, no real images, but brain segmentation maps, these do better than everyone. Now that to us was surprising. And it's also encouraging because that means that you can start looking at training models without being very, very careful with what data you use. But of course, there's a bigger question here, which is how do these models do when we deploy them to modalities they've never seen, right? That's what we care about. And so here's what happens. Here we're registering T1 to PD, so it's never seen a PD modality, really. Or we register T1 to T2, and networks have never seen that combination. And the classical models still do well because the classical models, they're not learning based, so they don't really care what existed in your data set. They lose a little bit of accuracy because when you're going across contrasts, there's less information shared. The voxel morph models, though, and any deep learning model that we try, completely collapses because it's never seen this combination of modalities before. So as per learning strategies, they won't work. But SynthMorph just continues to do really, really well. And the reason is because SynthMorph has completely ignored the actual contrast, the actual modality. And instead, it's focusing on extracting sort of common anatomy and matching it up. All right, now, as we're developing these models, and so this is one that I'm really excited about, right? Because now we're achieving really fast runtime, no data really needed, which is pretty cool. So now we can start deploying these on any modalities and so on. But there's still something that keeps nagging at us, and it's been nagging at registration for decades, which is the all-important hyperparameters. Now, this is endemic in machine learning and optimization. There's always hyperparameters that we have to deal with. So here as an example, I'm choosing this one hyperparameter that's always been a plague on registration, which is the one that balances how much do I care about matching the images and how much do I care about regularization. And people have come up with all kinds of strategies to choose these. A lot of the times it's manual. When in my PhD work, we did a lot of manual search. It usually goes something like this. You try out a bunch of different values, then you train your models for these different values. So you take over a lot of GPUs, then you look at how well these models perform. You realize you probably tried the wrong range, or you tried the right range, but it wasn't quite fine-tuned enough. And so you start the process all over again, okay? And this is painful. It takes a lot of GPU hours. It takes a lot of human effort time. It's affectionately called graduate student descent. And it's one of the really painful parts of doing research. And there's another problem which hides underneath, which is that we look for the optimal hyperparameter value. But it turns out there isn't one. Most of the time, these hyperparameter values don't actually transfer. And this is something that we haven't really explored enough in the community. So here is the optimal hyperparameter value for the GSP data set. Okay, on the x-axis, you have different hyperparameter values. Y-axis is the dice for those hyperparameter values. So, okay, the optimal one is 0.25. I found it. Now I can do all my analysis with this hyperparameter value. It turns out that's not really optimal because here's the optimal hyperparameter value for the MCIC data set. Why? Well, the data is slightly different and the population is slightly different and so on. Well, here's the optimal hyperparameter value for the abide data set. Here's actually the optimal hyperparameter value if I only care about the hippocampus. It's different than if I care about the ventricle. And that is sort sort of something that's really difficult to see if you choose one hyperparameter value, or worse yet, you just go to the original paper, take that optimal hyperparameter value and use that, right? You're not going to see that you're using suboptimal value in your analysis. So we thought it'd be really cool if we had a piece of software where a radiologist or a clinician can just tune or a researcher can just tune this optimal this hyperparameter value, and in real time, the software should give you the best registration under that optimal hyperparameter value. Of course, we can't do that nowadays. What we would need to do is for every hyperparameter value that's tried, we need to train a new model or hope we have a model trained or something like that. So here's our proposal. It's called Hypermorph. And the idea is we're going to train one large model, okay, just one, instead of all the different models. And this model will be aware of the hyperparameter. It will take it as input, right? Here's how it works. Here's a simple registration network, like the ones you've seen in previous slides. Take two images, register, get the deformation field. And now I'm going to add the deformation, the hyperparameter that I care about. Now, this could be any hyperparameter. I'm focusing on the one that balances the loss terms. And so I'm going to give this as input to the registration network. So, and I'm going to use it in the loss as well, just like I did before. So now when I give the registration network, say, a very low hyperparameter value, the registration network is going to say, oh yeah, I get it. You're not going to care about smoothness at all. So I'm going to give you a very non-smooth field. If I give it a high hyperparameter value, it's going to say, oh, I'm just going to give you a very smooth field. I don't care about the image matching too much. So the network learns how to adjust its predictions based on the hyperparameter value. It doesn't give us the optimal hyperparameter value. As I showed you, there isn't really an optimal hyperparameter value, but it's a network that knows how to adapt really quickly based on the hyperparameter value. The way we implement this is through a mechanism called hypernetworks, which are a really exciting tool, I think. Basically, it's this little network that takes in the hyperparameter value and outputs all the parameters of the registration network. Basically, it says, oh, this hyperparameter should give you this type of registration network. This other hyperparameter value should give you this type of registration network. Now, does this actually work in practice? So let's take a quick look. All right, we trained a bunch of different voxel morph models at first, just to see, what the normal process would be like. So in this case, we trained 10 different voxel morph models. Right? We spanned an entire range of the hyperparameter value. We did it on 3D images, so it took a very long time. It took about 40 GPU days in total for all 10 models. All right, so it's a lot of work. And we have quite a lot of expertise with running voxel morph, right? So we kind of knew exactly what to look for. And then we trained this one single hypermorph model. And it turns out that this one single hypermorph model can mimic all of the other models, right? Except we only need to train one. So in terms of training time, now one hypermorph model takes a little longer than a single voxel morph model to train, about 1.5x. But of course, we need to train 10 voxel morph models, right? 10 baseline models, at least. Most of the time, you might train a lot more. And that's compared to a single hypermorph model. So it's a lot faster in terms of GPU time. But what I can't show you in this graph is how much of a headache it saves you to train a single model that approximates this entire landscape of registration. Okay. So let me show you. So I've shown this before, but now this is actually using our hypermorph model. And you can see how as we tune the hyperparameter, it goes into our registration network. It decides what the optimal registration network is for that hyperparameter value, and it gives us the registration result all in one shot, right? So now we can actually employ this very smooth, precise tool that anyone, a radiologist, a clinician, a researcher can use to get the optimal value for their image pair. But it gets much better than that. we can actually automatically tune the hyperparameter value now. If we get a new data set, say the UK Biobank, and I have some validation data, some annotations, some structures that were outlined, I can now automatically, with gradient descent, choose the optimal hyperparameter value to optimize my validation. And so here's what that looks like. In just a few seconds, I can get the optimal hyperparameter value for Abide or GSP or MCIC. And that's really important because there's a big difference. You can lose 2 dice points if you just choose the wrong hyperparameter value. If you're using different imaging modalities, again, different hyperparameter values that you should use. If you're using, cross-subject versus within subject, different hyperparameter values. If you are looking at different structures you care about, again, different hyperparameter values. Now, this entire thing can be achieved with a single model, right? That's the really cool thing here. You don't have to train different models with different structures and so on. And so this is another direction that I feel like with classical models, we can really do this. But now we can do this with these hyper networks. We can very easily tune this hyperparameter value, opening the door to sort of some very precise tuned analysis. All right, so I got a 10-minute warning just now. I have one more short section, which is probably about 5 minutes, and then I can take questions. And this is the one that I think was mentioned in the introduction, template construction. And so this is one I'm really, really excited about. The question is, okay, I have this data, I have this registration algorithm. How do I register everyone to a template? I don't have a template maybe. And so we could build templates classically, but they took a long time. You would have to align everyone to some common original guess, average, realign, re-average, realign this, re-average. It took a really long time to do this well. So how does that change with registration networks? Well, if you look at a registration network, it's really learning something about your whole data set already. Somewhere in that network, there's this hidden information. And so we thought, well, why don't we just, when we feed the images to train the networks, instead of feeding a template and an image, a template and an image, a template and an image, why don't we just learn that template? We tell the network, listen, as you're learning your parameters, learn one more thing, the optimal atlas. So very little actually changes in practice. It's the same architecture. It's almost the same loss. We just add one term. But now we're training the network so that it learns what the optimal image is to register everyone to. So this is the sort of template that you get from our T1 images. But then we thought, well, this is cool, but we have very diverse data sets, different ages, different sexes, different diagnoses, and so on. Can we learn a conditional template, one that responds specifically to the attributes we care about? So say we have a 45-year-old female with Alzheimer's diagnosis with a particular gene mutation. Can we get the optimal atlas for that patient? Because then we can do these very fine scale analyses of how different is this patient from the atlas and so on. And we can do this in a continuous way, right? We don't have to learn 17 different atlases. We can just learn one function. And so this function takes in some attributes that we care about, age, Alzheimer's diagnosis, whatever you want, and it learns the template to match up the subject. So here's how it looks like with age. On the left, you have young subjects. On the right, you have older subjects. Let me show you a video. This is as the brain ages in our atlas. I'm going to show it again. It's a very sad video in some sense. You are getting this atrophy as a prevalent effect, right? So the ventricles are growing, the cortex is shrinking, and so on. But the remarkable thing is that these networks can learn this from the data. We didn't have to impose these things on our structures. We can also mimic behavior that we know from literature. Hippocampus shrinks, the ventricles grows, and so on. But the really cool thing is that now we can look at new data sets that maybe were hard to atlas before, and new entities, not just image atlas. or segmentation atlases. So we looked at pediatric data where a lot of things change in the first few days of life or the first few months of life. There's myelination that changes contrast. There's all kinds of cortex development. And so this is an ongoing project with Lila Zoleh on building conditional atlases for pediatric data. You can start bringing in adversarial networks to sharpen your atlases or to make sure that the segmentations are consistent with patterns that we expect and so on. And I'm very excited to apply these methods, and we have ongoing projects on going back to those original projects. Can we build atlases of change? Can we build atlases that show how a brain will grow in young patients, how a brain will atrophy in older patients? So atrophy maps or disease change maps, how white matter disease spreads through a patient as a function of attributes we care about, as a function of someone's diagnosis and sex and so on. All right, so I'm going to close off by saying this was obviously a lot of work from a lot of people, and I'm really, I'm really thankful to them. They take all these sort of directions that I think are not just about improving accuracy, which is important, improving runtime, but really doing things that we just didn't really either do before or it was really difficult, right? So we combine these classical intuitions with neural networks to get these fast networks that allow us to do all this research in new directions. So with that, I'll take questions. Thank you.
Thank you very much. On behalf of all of us, I'll give you a clap on behalf of the audience. We do have some questions. There's some in the chat. Please post them. I'll start from the top. I have plenty, but I'll take these ones first. One from Vinod, amazing work. Did you also plan to test structural contrast with EPI, fMRI data, which usually have distortions due to inhomogeneities? And I think this came in the first part of your talk about registration.
So the answer is yes, absolutely. So I work in a lab that is heavily uses these sort of modalities, and we're actively doing research in both registering across these modalities, but also dealing with inhomogeneities. And so we do things like simulating them in SynthMorph or trying to sort of simulate them as data augmentation and so on. So definitely an active area of research. Yeah.
Thank you. Next question from Thomas Wolfers and Eston Leonardson. Wonderful talk. Quick question regarding the last part of your talk. Does it make sense to build conditional atlases based on multiple factors in addition to age, for example, genetics?
Right. Yeah. So we do that. We focused on age because it's the strongest effect, and it's one we could convince the NeurIPS crowd about. But we are definitely very excited about multiple attributes. And so actually in the paper we use age and sex, but I really cared about these Alzheimer's prediction maps and so on. So there we're looking at ApoE, allele, and diagnosis and so on. Same with the young pediatric patients. Different ones might have different diagnoses, and that or treatment is something we're hoping to look at. So definitely really exciting area. In fact, I think that's where the promise is of that whole Atlas framework.
Great, thank you. Another one from Luis Alberto Sotomayor Neto. Sorry for mispronouncing your name. This is an awesome work. My question would be, does voxel morph work well in highly non-isotropic settings? For example, 1 millimeter by 1 millimeter by 5 millimeters.
By 5, yeah. So that was the clinic. I rushed through it. That was this clinical section I had a couple minutes. So our stroke data was actually 1 by 1 by 6. And my opinion is that with a little care, it works better than the classical methods. And I think it has to do a lot with the fact that it doesn't get stuck in as many local minima. And so we saw a lot. It's really not that it improves all the images by 2 dice points, but rather that it avoids failure cases. So there are classical methods that, at least in our experience, it was hard to register some of these subjects where you had really big changes and it was really thick slices. And somehow the deep learning methods seem to get past that and fail in fewer cases. So I think that's definitely a domain where it can make a difference.
Great. And I'll take the last question from Paul Thompson, who said, and fitting that he's the next keynote speaker, said, extraordinary talk. Congrats, Adrian and team. I was really excited about your slides showing how much training data is needed to get a good model. If groups use your code, do you recommend that they train it themselves on their data, or should they use a pre-trained model?
So I think it depends on the data. We have started releasing these Morph-based pre-trained models. The reason is because we find that they tend to be quite robust across completely new data sets. So people have tried to register things that, honestly, some things I've never heard of, some imaging of chemical reactions and things like this. And so it's really exciting to see new modalities and new domains being used, but obviously we can't pre-train on that data and release. And so we've generally are releasing these general models like Morph that hopefully give people a very good initialization. Most of the time, we do recommend that people fine tune if they are dealing with substantially different data. Now, if you're dealing with T1 MP-RAGE MRI or things like that, that are very popular in neuroimaging, we definitely have well pre-trained models for that. So yeah, and I do see a couple of questions here. Sorry, I'm just seeing the chat now. So just as a couple of other quick answers, rigid registration, originally we assumed you've done it just because it simplified our life, but you can really combine rigid or affine registration with the dense deformation field. You can combine it in one go and with different amounts of accuracy, but it can be done. And the last thing that is not a question, but a suggestion, just a completely side plug, and to tell you that we are running a new journal that is very exciting and really, will accept really high work, Melba, and it's running a bunch of different special issues from Mackay. So I really encourage you to submit to Melba. All right, I hope that was a good
there's probably some news about that coming later. Thank you very much, Adrian. It's really excellent work, really innovative, and I think it's really makes a big difference to the field. So so just thank you once again.
Thank you. Thanks so much.
And I hope you can stick around for the panel discussion afterwards. Your presence would be very welcome on that. So now I'm going to hand over to the chair for the next part of the session, which is Ahmed Abdul Qadir, and he'll take us forward into the next session. Thanks again, Adrian.
Thank you. Thanks for having me.